Here I have the two output files opened up for the protein ligand complex, for the Autodock4 results and the Vina results. First, I'll be looking at the Autodock4 results. In the first line here, what we're looking at is the receptor name, the 5EY0 pocket. So we're looking at just the pocket site area of the receptor, as that is the area that we docked. Here you see a list of atoms, and this goes from 1 until 418. So this entire thing is the whole structure of the receptor. So there are 418 atoms total. Each of them corresponds to its own atom type, like carbon, its own residue, could be valine, glucine, serine, etc. And it's showing its coordinate numbers, the XYZ coordinates, in an open space. When we scroll down here, then you see het atium. That's just another synonym to say atom. And this line is talking about the water molecules residue, HOH, but it is within the pocket site area. In the Autodock software, we initially removed the water molecules, but only the ones that is in a free open space. When it comes to the water molecules that's near in the pocket site, we count this as part of the interactions for the scoring function in order to get the binding energy score within that equation. There's the next line of code that says model, and we can see that there are 10 of these total. So what that means is we have 10 unique docked poses for one protein ligand complex. This is our run 1, for example. This is the result for the free energy of binding, or the binding affinity number. So this is minus 4.14 kilocalories per mole. And it's showing how it did its calculation. So essentially you have these different types of energy and interactions that happen within the pocket site where the ligand interacts with the receptor. So you have your intermolecular energy, so this could be van der Waals, the hydrogen bonds that I mentioned earlier with the water molecules for the hydrogens, desolvation energy, electrostatic, torsional energy, etc. The software just calculates each of these numbers, and when you add these all together, then this is what outputs as the final result. And it also tells you what the inhibition constant is, which is this number. So generally a lower binding energy as well as a lower inhibition constant results in stronger binding interaction. This next line of code talks about the translational and transformational movements that the ligand is going to move in an open space. It just talks about how it rotates within an open space. So these are like its coordinate numbers. Keep residue numbers equal 1. Keep the same formatting and orders of the different atoms. We have 6 active torsions. Torsional, or the rotatable bonds that we set to be active. So in this example, the highest we could go was up until 6, and this is telling the different atoms within the ligand of what areas are inactive versus the ones that are active, so I versus A. These are the ligand atoms, has its own coordinates, its van der Waals, and electrostatic energies. So it has the list here of the new transformational or translational area, how it moves. And then this part of the code talks about the branches and roots, basically a side chain or another part of the molecule that is connected to its main structure. Now I'm looking at the Vina file, so similar concept with the previous file, but it's a little bit different. So again, there are these different docked models, so from 1 until 9 in this case, because that's the default number in that software. Here for the Vina result, what these values represent is the first one is your binding affinity, which in this case would be minus 6.4 kilocalories per mole. And these two are the RMSD values, or the root mean square deviations. Let's look at the model 2. So the first one had a 0, and here it has some number. So what the RMSD indicates is how much deviation there is compared to the previous initial pose. So it would be these numbers here. The first value here is lower bound RMSD, and this is computed by only considering the movement of the non-hydrogen atoms of the ligand, comparing the initial pose versus the new pose and they become superimposed with each other. So there's going to be some kind of distance or deviation between these two structures, and that's how they get this value. Third one here is your upper bound RMSD. Naturally, this is a higher number because this will include the hydrogen atoms to the ligand. So it represents a broader comparison, and that's how they would get a larger value. So these two become the outputs for Autodock4 and the Vina software respectively. And with these different docked poses within these files, they are going to be inputted into the graph neural network separately, so that it can produce a more accurate results than what these traditional docking softwares conclude. We do have one limitation with our Autodock and Vina software, and what this has to do is with the docking code, which relies on the AD4 parameters.dat file. So here they have a list of all the different types of atoms that it's able to read here. But in the case of the receptors that we've worked with, we do get some errors that it cannot read certain atoms or metals such as copper, potassium, or nickel as an example. So that limits our data set as to which receptors we're able to use so that this software is able to read and make it work. In order to fix that, I mean, that would require looking into the code of the software itself and see how we could do some modification or adjustment. But even doing so brings its own like Python errors if you try to mess with the files here. So we just kept the system parameters at default and just go with whatever worked for us in order to build the 400 total data set.